So let's talk about the power flow in Thyristor rectifiers. So actually the instantaneous power or average instantaneous power is here, and if you take the average of that power, it just gives you the average power. And I can rewrite that equation, using the voltage equations that we just found, and that is like the output power, and there's no power dissipation inside the converter. And you can see the power, okay, the real power is as a factor of cosine alpha, and because of that conversion ratio I have 0.9 Vs in my calculations. And let's have a look at the current waveform. And in the last video we discussed it is a square waveform on the grid side, but it is slightly different than a diode rectifier. So this is our line voltage, right? This is our line voltage, and this is our source current. So it is, yes, it is a square waveform, and that is 180 degrees, but because of if you just let's go back and again clean that part. Okay, if you look here, because of the delay in the firing angle when that thing is alpha, the zero crossing of that current is also delayed by alpha, and this is what we see here. So the square waveform, but it is shifted by alpha here, right? And if you just take the fundamental of that thing, and if this is like Is, and you can say the peak value is 4 over pi of that Is value, okay, and if you take actually if you divide it by square, this is the peak value, if you divide it by square root 2, it will just give you the RMS value of that fundamental. But not even it is changing. If you take the fundamental component, you see there is an alpha of shift here. So if you remember, no, actually I have the slides. So for harmonics and I1, so THD, it is still a square wave, and the THD is same with a normal square wave. Even it is shifted, it is just related to the current waveform, so it was around 48.4%, right? And the magnitude of I1, actually again it is the same as the square waveform, but the thing is slightly changed with respect to diode rectifiers with power factor and displacement power factor. Remember, displacement power factor is the angle between the fundamental of the voltage and current, and since we have here, so alpha is the displacement angle between those things, and displacement power factor is equal to cosine alpha. So actually if I operate it at zero firing angle, so it will be a displacement power factor of 1. If it's operating at 90 degrees, so there will be no output voltage, so there will be no real power transfer, so the real power will be 0. If alpha is larger than pi over 2, the output voltage, remember it was like that, right? So let me get rid of myself. So this was ID, this is VD, this is minus VD. So this is the positive voltage range, and this is called like the rectify operation mode, and here it is the inverting mode. So in this region, you can still think about it from the load side. So you have the current like that, but if your output voltage is negative, so that means power flow is from here, right? So not your supply, supply is giving power to your load, but your load is supplying power to the grid side. I mean, it can be like a DC machine working in the generating mode, or that can be, I don't know, a PV inverter. But in order to have that kind of operation, you need to have some kind of active load, active source in the secondary side. And actually you can see it here in the power factor. If alpha is larger than pi over 2, your power factor becomes negative. So a negative power factor implies your power is not flowing in that direction, but it is flowing in the opposite direction, right? So again, you can write power, or for real power factor, remember it was the ratio of the IS1 to IS, and you can write, because our grid voltage is constant and it is purely sinusoid times dPF, and it is 0.9 cosine alpha. So the real actual power factor is slightly lower than the displacement power factor, because displacement power factor only takes into contribute the fundamental component, but the real power factor is larger than that one. Actually, I think I have a better graph. So here you see the comparison. So this is our real power flow. So whenever it is here, and if you just look at the fundamental component, okay, so when alpha is equal to 0, dPF, displacement power factor, will be 1. So 1 power factor means power is equal to S, apparent power. So they are at that point, and you can say, Q, remember from the previous year, P square root is equal to S, okay. And actually at that point, this is a unit power factor from the displacement. And as you increase the power rating, yes, at 90 degrees, whenever it is 90 degrees, your output voltage will be 0. But if you look at the current waveform, it will still have that, square waveform. So it is drawing some current, but that current is not doing any real work, but all the apparent power, like in the form of voltage and reactive power. So you are just getting energy, then you are giving it back to the grid at that operation. So no real power is transmitted to the load, but it is like fluctuating to the converter and to the source grid. Okay. However, if you go that way, right? So at that other point, maybe all power is coming from the current source. So if you have, I don't know, the grid here, okay, and if you have the load, again, it can't be a passive load for this operation, but for here, the power flow is from that direction. Okay, again, the reactive power reduces and reduces. So at that point, you are just sending all the power to the grid side. So it can be like a DC machine working as a generator. It can be a PV system, that kind of active load. And actually, please have a look at that simulation file. You can run it at your own browsers, and you can check how the voltage and current waveform changes. And that line, actually, it's all calculated with respect to the fundamental components. And this is 0.9, this is the 1, and you have the third harmonic, fifth harmonic, other harmonics. And actually, if you calculate all those things, your real apparent power is slightly larger than the first component of that apparent power. Okay, cool. So now let's move to another topology. Actually, it's the same topology, but just with resistive load. I would like to discuss a couple of conditions. So now, again, they will be operating from S1 to S2 and then S3 to S4. But now we don't have any, ideal current source, or we don't have any inductive component. We just have that resistive load. So resistive load means whenever your output voltage, it will be identical with your current. We don't have that case for current source, but with the resistive, so your current is going to be negative at the instant that voltage just dropped to negative. But actually, if you look at here, it is not possible to have negative current because they are behaving like diodes. Even if you apply some gate signal, so there is no path for them to carry negative current. So let's have a look at the voltage waveform. So because of that thing, let's start here. So you fired it, and then it just starts conducting from one point to another, okay, and that instant, okay, at that instant, so now you are supplying it through here. Now your output voltage gets smaller than 0. So, but there is no energy storage element on the secondary side, so the current would like to go to negative. Okay, this is the same as the voltage and the current, they have the same waveform, but it cannot go, the current cannot go into negative range because there is no path for that one. So at that instance, okay, all switches are off. So there is some part which you are not drawing any current from the grid, and next you apply again, and then you have that kind of waveform. And if you think about it, what is the average of that one compared to the with the current source? Is it like A lower, B same, C higher? So what is the average voltage in this case compared to the one with the ideal current source? Okay, I will just give a couple of seconds. And of course, in the previous case, our output voltage is going below 0, and that has even more effect to reduce the output voltage. Now we don't have that negative region, so it doesn't, again we still have the 0 voltage, but at least it doesn't go to negative voltage. And because of that, for the same firing angle, the average voltage of that case with a resistive load is actually higher, right? So actually, let's calculate it for that one. Again, get rid of myself. So here, it is the same logic. I will get that area, right? But in the previous case, I was taking from alpha to P plus alpha because it was going down to here. But now this part is 0, so I will take my integral from alpha to P, right? So let me write it here. The average voltage will be equal to alpha to P times, let me write it the same one, square root 2 Vs sine omega t d omega t, and either you can multiply it by 2, divide by 2p, or divide that thing by p. And actually when you write that one, square root 2 Vs divided by p, right? And now remember, that was, I'm not writing in full, but this is minus cosine alpha, and minus it becomes cosine alpha, right? And write cosine alpha, and then I have the cosine p term that becomes minus 1 minus minus 1, and it becomes 1. Okay, so that is the waveform. And actually you can still double check it whenever alpha is 0, so that is equal to 1, so it is 2 square root 2 Vs divided by P. It is the same thing as a diode rectifier. And actually as you increase alpha, that whole value is going to get small and small, and actually you can get another voltage, but the voltage characteristics is slightly different than what we have with the ideal current source. Okay, so that's our equation. So now let's look at the RL load. Again, I don't get into the much details of the waveform, but I would like to discuss continuous conduction mode or continuous current and discontinuous current. So here we have the same schematic, and instead of just resistive component, I have inductive element in the load as well. And again, if L is like really large, then that load can be simplified as an ideal current source, but now L is not that big, and because of that the output voltage output current can go up and down. So now let's look at that value. So let's start with alpha. Now I have the voltage, right? Again, I'm not getting into the details. That is another thing I would like to emphasize. So whenever you are applying some voltage, of course depending on current waveform, and I can find the peak value depending on the resistive component, whatever. But anyway, at first you have a large voltage and you are increasing your current, and in the second loop then you are reducing, okay, but actually your current doesn't need to reach to zero. Remember, if it were an ideal current source, this will be a horizontal line, but now we have some ripples and now it is reducing. But let's assume, we will talk about the other case, but let's assume now it didn't reach to zero, right? So now I can fire the next pair, then it will start all over again. This is not the grid voltage, this is the load current, okay, not the grid current. Grid current will be the reverse of that thing. So if you draw the grid current with an ideal current source, it was like that, and with that one it will be more or less like that, with some sinusoid distortions, right? Anyway, so this is our load current. So my question is, what happens if your average current is reduced? If that one is reduced and that one is reduced, so it is getting smaller and smaller, right? So then again, the problem is, if you just look at here, that current cannot be less than zero, because that implies some current to flow either that path or that path, but it is not possible, as those are thyristors. Okay, so what will happen? It is similar to what we had with the resistive load. Yes, at that point you can start charging your RL load. At some point it will start discharging, and that instant, and if you're firing, again that thing happen after your firing, but let's say your firing angle, okay, is larger than that beta angle. So again, it is similar to resistive load. At that point your current reached to zero, okay. So once it reached to zero, all the thyristors are off. Let me write it here. So during that, all thyristors are off, okay. So there's an instant where your load is disconnected from source, the current reached to zero, and it is just waiting for the next cycle, okay. So you have that kind of operation. So actually we will see that in DC-DC converters, that is called the discontinuous current mode or discontinuous conduction mode. So the load, on the load, I have some positive current for some region, and I have some zero current. And because of that jump, I mean, if you look at the characteristics of the continuous current and discontinuous current for the output voltage waveform, so for that the output voltage is exactly again same as the ideal current source. So in ideal current source, we just ensure it is always in the continuous current mode, continuous conduction mode. But if it is an RL load and if your average value of the load is less than the ripple value, you can have that kind of output voltage. And I mean, again, compared to, let me ask that way, compared to continuous conduction mode, does the average voltage in this continuous conduction mode, is it higher or be lower, right? So again, if it were in the continuous conduction mode, we will have that negative voltage up until the firing distance, but now we just get rid of that one. So in the discontinuous conduction mode, for the same firing angle, the output voltage will become higher. Okay, so that is quite important for control, especially if you have working at lighter loads. Your voltage becomes non-linear. Okay, you don't have the same equation with the continuous conduction mode. As a result, your controller should be either measuring the output voltage or current. Just applying 30 degrees of firing angle will not give you a specific voltage. It depends if your converter is operating at continuous conduction mode or discontinuous conduction mode. And let's talk about, you can do the same thing, you can do the same kind of, let me show with that one. Okay, here if you just use the resistive load, it is, the output voltage is not a load to go to the negative voltage, right? And actually I can do the same thing with a freewheeling diode, and we did it with a single thyristor. So here I have my 4 thyristors, and to the output I just connected a freewheeling diode. So again, that voltage, that output voltage, cannot be less than 0, because whenever it is less than 0, that diode will get into the forward conduction mode and it will freewheel your RL load in that cycle, right? So now let's try to plot the output voltage. Actually, I think I didn't put it here, but it will be the same with that one. Okay, so at first you will be operating until here. So this is the freewheeling diode. So whenever it wants to go in that point, actually the diode is on in this region. Okay, so it will just discharges LR load, and until you fire the next set of thyristors. Okay, so again, the output voltage is not allowed to be negative for this case. Okay, and what are the advantages and disadvantages? So advantage is your output voltage now has less ripple, because in the previous case you have the maximum positive voltage and you have the negative voltage, and the difference between them can be quite problematic for your load, insulation of your motor, etc. But once you have the freewheeling diode, actually you are limiting the minimum voltage with 0, so your ripple can be smaller. And disadvantage, of course, as a disadvantage, instead of using just 4 thyristors, you are using an extra diode, which increases the cost. But actually we can overcome with that cost. So how can we make this circuit cheaper? So if you think about it, whenever the current flows, so I have 2 thyristors in series, and actually if I just they are like 2 switches that you can control in series, right? So I can do the same logic by just putting a single switch, and if the other one can be like master, instead of having two masters I can have master and a slave, and basically I can do that by changing those things, but not with a thyristor but with a diode. Okay, let's say you replace that one with a diode, so whenever you open that thyristor, actually it can still flow like that, it will not affect its operation. And the same thing can be applied for that one. So if you are opening that one, or if you are opening that one, so basically the other one can be changed with a diode as well, right? And as I have two series diodes in that direction, so they are, if they are ideal, they are just checking that voltage. If that voltage is less than 0, both of them will be get into the conduction mode, and you will have the freewheeling effect. So basically you can get rid of that thing. So our circuit becomes something like that. So in the previous case I use 4 thyristors plus 1 diode, or in the first case I am using 4 thyristor. So this was the default one, this is the freewheeling one, and with that freewheeling one I am using 2 thyristor plus 2 diode. I mean, actually if you compare the cost of that one and that one, that is even cheaper than the original solution, and your output voltage is limited. So I can have, you know, 2 diodes connected like that. Whenever my current flows, it flows through here, and whenever it is in the negative path, it just flows like that, right? And by just controlling Q1 and Q2, you still have all the voltage control, and D1 and D2 works as a freewheeling diode. Okay, but as a disadvantage, okay, so as an advantage, the ripple voltage is smaller, and also the cost is slightly reduced. But at a disadvantage, so if this is your output voltage, now output voltage has to be larger than 0, so it is no inverter mode. So even if you apply a larger angle than pi over 2, it will not be able to supply negative voltage. Okay, so it is a single quadrant rectifier as a disadvantage. Okay, I think that one is the same idea. I mean, this is another version. Instead of putting 2 diodes in series like that, you can, you know, have 2 diodes here, and either you can keep the freewheeling diode to have that path, or, you know, depending on load, you can actually get rid of that thing. So this is another version of that one. Okay, so let's stop here for now.